to the second class. We have Pak Endra here. And Pak Zul, are you here? And I hope everybody enjoy the short rest and come back fully charged for the second lecture from Pak Endra. Pak Endra is a big guy in volcano monitoring or GPS deformation monitoring because he has so many researchers, he has so many publications, and he is very well known for his work in GPS deformation. And literally, he is also a big guy because he's much taller than any of us. And so the second section, I will give the pressure for the screen and time for Pak Indra. Please, Pak Indra.
Okay, thank you, Pak David, for introduction on the big guy. Well, yeah, I'm just a little tall, but I'm still shorter even than Michael Jordan if you play basketball. But I'm a little bit higher than Messi if you compare me to Messi. So anyway, thank you, Pak David. Good afternoon, everyone, participants from Indonesia. And good evening and good morning for participants from another country, wherever you are. And previously, Pak Irwan has already mentioned and explained to us in detail about the deformation and the modeling using geodetic instruments such as leveling and GNSS, and some results in Sinabung and Agung. And in this occasion, I will not explain in detail again. Instead, I will okay. Oops. Instead, I will refresh to us about the basic information on what is GNSS and how to model the volcano. And as Pak David mentioned, my name is Endra Gunawan. I'm from Global Geophysics Research Group. Same group with Pak David, Pak Zul, Pak Andri, and previous speaker yesterday, 2 days, I guess 2 days ago, I guess. And well, this is, if you look at the figure here, my presentation here, this observation was, we collect data as shown by Pak Irwan in 2018, 2019, end of 2018 until mid of 2019. And during that time, we are happy with the situation. We are very delightful with the condition because on that time we don't have pandemic, coronavirus pandemic. And sadly, right now we experience a second wave, which is very, very destructive, and sadly, some of our colleagues has already infected and affected by the pandemic. And this situation influence our, if we are love to work in the field, then it's very influence our field observation. And in this slide here, the left, can you see my pointer, Pak David?
Yes, Pak Indra, I can see it clearly.
Okay, if you look at this left figure here, the one that I point out is a GPS antenna maintained by the Geological Agency. And if you look into detail the previous presentation by Pak Irwan Melano, there are basically two GNSS network, I'm sorry, in surrounding the Agung volcano. The first, the existing one, is the GNSS network by the Geological Agency, and starting from 2018 up to mid of 2019 is our newly installed GNSS station. We installed 4, so that will be on the right side here. And because the GNSS basically receive signal from the satellite above outer space, so we have to put antenna free from obstacle. And here you see we collaborate, or we have our antenna. Okay. I'm sorry, someone knocking my front door, so I have to apologize for that one. So the right side is our new antenna on our new network. If you look at in here, the problem with the GNSS installation, as you can see also in the seismic installation in last 2 days presentation, and probably tomorrow and the next day presentation by Pak David and others, is the electrical problem. So we are facing lack of electricity. Instead, our instrument need some power. So we have to use a solar panel and external battery. So this situation is our what we face in the field. And in the surrounding the Agung volcano, we installed 4. And if you look at the data as shown by Pak Irwan Melano, another 5 GNSS network available surrounding the volcano. So in total, basically, we have 9 collaboration between the newly installed GNSS by ITB and the existing 5 by Geological Agency. Now I will talk about some introduction on the GNSS, which stand for Global Navigation Satellite System. And historically, the satellite system, the first satellite system, it's called Transit. It was installed commercially used in 1967, and it's orbiting above 1100 kilometers altitude. And because of this height, it's affected by the gravity field than the much higher, because it's much closer to the Earth. And it's transmitting at 150 and 400 megahertz, which is more susceptible to ionospheric delay and disturbance than the higher one. And it was discontinued. The transit system was discontinued at the end of '96. But after the first system, transit, in 1967, another system called NAVSTA, or navigation system with timing and ranging, was introduced in 1973. And the complete name, or the longest name, the name itself is NAVSTA GPS. And so this are maintained by the United States of America. So if you name, or if you mention GPS, or global positioning system, then it will refer to a station system owned and maintained by the United States of America. And similar to technology such as your mobile phone, or probably motorcycle, every technology will be refreshed and updated. throughout time. And for example, the Block 1 satellite was in 1978 and 1985 with the failure of launch one time, and average lifetime is 8 to 9 years. But the next generation, there are next generation after the Block 1 satellite. There are the Block 2, Block 2A, Block 2RM, 2F, and 3F. So basically right now we still have some operational satellite except for Block 2A. So we have Block 2R, 2RM, 2F, and 3 and 3F satellite available in the outer space. This GPS satellite. So we called this segment in the satellite itself is the space segment. And if you look into detail, the difference in technology, for example, the Block 2A is only have L1 frequency, but the later generation is like when you have, like I mentioned, a mobile phone. Before the first generation, the mobile phone is only 2G, and then the next generation after 2G is 3G, and then the next generation comes with 4G, and right now we have 5G. It's similar to that one. So the 2R, for example, it has L1 and L2 signal, but the latest one, if you look at GPS 3, it has not only L1 but also L5 in here for 2F. And also the lifespan, because the satellite is out of reach in the outer space. Before the 2A, for example, is only 7.5. Right now, the latest generation is longer, much longer than that, 15 years lifespan. And it's only recently launched last 3 years ago in 2018, the latest generation. So as of October 2019, in total, there are 30 operational satellite GPS, because it's the GPS system, this segment here. And the satellite takes about almost half a day, 11 hours, 15 minutes, and 2 seconds to orbit around the Earth. And if you have a space segment, then and someone must be maintain that satellite, and it's called a control segment. So the master control station is located here in Colorado here, the red star here. And some Air Force monitor station is spreading all around the world here, as shown by the blue circle here. And basically the duties of this control segment is to track the GPS satellite in the outer space and to monitor the transmission, to perform analysis, and to send commands data to the satellite constellation. And the third segment is our part, that is the user segment. So the satellite segment is the outer space, space segment, and then the control station is the one that maintains the satellite itself. And now the third segment is the user segment. It is basically most of us involved and contribute to this segment. So either like it or not, either you realize or not, you have used GPS. For example, if you're traveling from one point to another point by airplane, for example, and those airplane they have a GPS system to travel. And the simple application is that if you I believe 99 or if not is 100% of you have a smartphone, and you have one of the application already installed in your smartphone, and you want to travel or picnic, recreation from a point to another point, or to travel from one city to another city using your smartphone as a guidance, then your smartphone basically have a GPS receiver. And this is not just recreation or in the airplane, but in the United States, for example, they already applied the GPS for the agriculture, environment, and even for the timing. And why? Because the timing for GPS is atomic clock. So you have a very precise and very accurate time from GPS. And if we come back again to the first term, GNSS, or Global Navigation Satellite System, and GPS is one of the station, then right now there are other satellite system. For example, Beidou maintained by the Chinese government, and the IRNSS by Indian government, and GLONASS by the Russian government, and QZSS by the Japanese government, and Galileo by the European Constitution. So right now we have, other than GPS, we have another option. GLONASS, as maintained by Russia, for example, basically start from 1982. So it's comes after the NAVSTAR GPS. And right now we have the generation of GLONASS K2. And this is still in development, and the K is in orbit. And almost similar to the GPS, the period orbit is 11 hours and 15 minutes and 44 seconds, slightly almost the same with the GPS. And another system called Galileo, or the European Global Navigation System, is designed basically by the and funded by the civilian European institution. And in 2002, the European Council agreed to launch European Civil Satellite Navigation Program called Galileo. So the name is follow the great scientist Galileo. And the two initial satellite launched in 2005, another 4 additional satellites in 2012, and service, we can use the service of the Galileo satellite in end of 2016. The next satellite called Beidou. So it's from the Chinese government. And the Beidou one, 3 satellites since 2000, year of 2000 up to 2012. And right now, the generation is Beidou 2. And it's operational in China since end of 2011, and from end of 2012, it has offer service for the customer in Asia Pacific region. And there are some publications that already use Beidou satellite, Beidou data for the analysis. And the next satellite is Japan, QZSS. Launched in September 2010, and the idea of the Japanese government launched this satellite basically to combine between GPS, the existing the pioneer satellite system GPS, and QZSS, which could significantly improve the positioning only in Tokyo, and most of because Tokyo is a big city and most of the economic activities happen in that city. And the last satellite system is Indian, or IRNSS. It was the first satellite launched in 2013, the second in 2014. But unfortunately, right now, we don't have any documents, official documents that about discussing or mentioning about this satellite. And even some publication, we cannot yet find any publication of this using the data of this satellite. So if you see this solid black line here is the GPS from the USA, and then this dot, this one is from the Russian or GLONASS, probably about 5 to 10 years after. And in the year 2000, for example, Beidou start to have installed, and then Galileo here. And this one only until 2012. So the end of 2012 or 13, GPS still, this is the y-axis is the number of satellites. So up to the end 2018, you can see that most of the satellites available in the space is GPS, and then followed by GLONASS, and then Beidou, and then Galileo. But if we look at by the early last year, 2020, so this is GPS, total satellites in constellation is 33 satellites, and GLONASS is 28, and Galileo total 26. But if you look at Beidou, for example, it's already 48. So during 5 years span time, the Chinese government has already increased significantly the number of satellites available in the space. So it's already more than 50% of the existing GPS. And this is the distribution of satellites in most part of the world. And this one GLONASS, Beidou, GPS, and then the left bottom part is Galileo. So the white means it has more satellites, more than 16. And we are right now, I'm in Indonesia, and for other participants from another country, you can look at by yourself. And in Indonesia, the total satellites that available in our space is Beidou, because it has more than 16. And GPS follow after here at most part of Java, about 11 to 12. And then Galileo here at some part, and the list is GLONASS. So this one comparison between those 4 available and which we can use. And if we look at because the GNSS located in the outer space, then we have to understand that there are errors. The first error is called multipath. It's where the signal is not a direct path towards our satellite, but it's indirect. So it's a reflection. And then the second error, it's called satellite geometry constellation. So basically we are user here, and if we are the constellation of satellite is on much like the left figure here, then we will have a better a smaller error and better data as shown by the PDOP, or position dilution of precision. But if we have most of the satellite is only on top of our position, then we will experience a larger PDOP. So this one, 2 error from GNSS, which can affect our data. And another is atmospheric reflection. So because the troposphere and ionosphere can change the speed of propagation signal, so the atmosphere refract the satellite signal. And in order to minimize that one, the first generation, for example, is satellite. In my previous slide, I showed that 2A satellite generation only L1 frequency, but right now we have L1, L2, L5, and And so in our part, in the user segment, so we have to use GPS receiver. So it's like you have a modern smartphone. So if you have modern smartphone, it has very good camera. It can receive a better signal, 5G, for example. It's similar to that one. So the new receiver, for example, it can receive more frequency, and it can minimize the atmospheric reflection because of the atmospheric reflection. And the next error is called ephemeris. So basically, the accuracy of GPS satellite is atomic, or 1 nanosecond for each clock tick. But because the inaccuracy of satellite atomic clock being synchronized, so the offset can be 2 meters. So if we have error in 2 meters from GNSS signal, we cannot do our analysis for crustal deformation or volcanic deformation. If we, from previous presentation by Iran Melano, we need accuracy of millimeter level. So to minimize the ephemeris error, we use ephemeris data. So by using this data available by the control segment, then we can get the accuracy of millimeter level. Okay, and then I will move to the slightly introduction to volcanic deformation. And volcano deformation caused by pressure change. It can be magma, but it can also be some hydrothermal change system. So it doesn't have to be magma. But those pressure change, we can see, or we can detect using GNSS, such as the one that show in this figure, or the one that's shown by the previous presentation by Iran Melano. And those kind of deformation, we need to understand what is just interpretation of what physical phenomenon happening in beneath the volcano itself. So using this data, then we have to understand what is going on and what is the beneath the volcano. And there are some model, for example, monkey, as mentioned by Irwan, spheroid, dike, and this will be, I think this will be my last slide. And if we look at the deformation resulting from each of those model, you can see that those modeling deformation has different impact. For example, if you use point source by Mogi, then this is the vertical, this is the horizontal. You can see that the deformation is more or less like this. But if you use a spheroid or yang, it has like this geometry like this, then there's some significant changes compared to the Mogi. And if you use dike, then it will be much different. So probably it's also adding more explanation to the previous question. So how many GPS we need to install, or EDM installed surrounding the volcano. If the idea is to, like Pak Irwan mentioned, to have a grid, but because of the limitation of our capacity having a GPS, then if we have a GPS or GNSS surrounding the volcano, and we can get some difference in the observation, then we can model and we can analyze which model capable of fitting the data. So that's the idea of having GNSS stations surrounding the volcano, not just only one side. Because if we have those GPS surrounding the volcano, then we can get a better view, or better picture of how the physical process beneath the volcano itself. And that will be my last slide. Thank you, Pak David, Pak Zul.
Thank you, Pak Endra, for a very nice presentation. I believe there are some questions from the audience, so we are moving to the question and answer session. So before I'm giving the opportunity to the audience, I would like to ask myself, because it was very interesting. So you mentioned about the development of the technology in the satellites, as well as the technology in our cell phone. You mentioned about the 5G and so on. So will it be possible in the future that perhaps we will become kind of moving a GPS station because of the accuracy of our cell phone is quite good enough, and perhaps someone can mining the data and using the big data to somehow monitoring the deformation by using a cell phone.
So okay, yeah. So we have to between GNSS data obtained from the cell phone and the one that used in the volcanic deformation, for example. We have to understand that the specification both are different. It's like if you have cell phone cell phone and then you use the cell phone to travel, and you knew that there are your cell phone capable to receive satellite signal, but the question is how is the accuracy? So in the technology used by the cell phone, if you check on the data itself, you can get 10 meters away from the original point. And well, because the technology is different. The one that we use in the volcanic monitoring, for example, we cannot use 10 meters accuracy to understand the physical process because it's too large. The signal, as Pak Irwan showed in his slide, probably only millimeter to centimeter level. So having inaccuracy of 10 meters away from the original point, it will be very inaccurate. And even so, if you look at the price, for example, smartphone probably 5 million rupiah, or if you put it in US, for example, 400 US or 300 US. But then the price of the GNSS receiver, which is used in this volcanic deformation, is almost at least is 100 million, or how many you can say, 8,000 or 8,000, yeah, 8,000 US dollar. It's more in technology. You cannot you can see by the price that the smaller price means the technology itself is it's not as reliable as the one that has higher price. So in that case, we cannot use currently we cannot use the GNSS system from the mobile phone. But then how about in the future? Well, I believe the idea of having a smartphone is to communicate and to help us to assist. So user doesn't need to have a millimeter level. Only certain people need a millimeter level, such as the one that we use in here. So that's why probably if I have the mobile company, I would not bring the technology to observe to have millimeter level into smartphone, because the price will be very, very expensive. And then who will be the user? Because that's the idea of having smartphone for 5 million. It's not that mandatory to have millimeter accuracy in smartphone. If you want to travel from one city to another city, so it's just need, if you use a car, you don't need to have accuracy millimeter level. It's 10 meters is fine because you know the location and you know how to go. But if someone, some company wants to bring that technology to smartphone, then the consequences will become the price. I think that's the one of the reality that we bring newest technology into some small device.
Okay, thank you, Pak Endra, for the answer. So there is still a big gap of what we can measure by our cell phone, right? With the current technology, or even in the near future. Yeah. Okay, thank you. So we'll move to the participant. If you have a question, I have one private message from Dian that she want to ask you personally. So please, Dian, don't be hesitant to ask your question. Yes.
Thank you, Pak David. Thank you, Pak Endra, for the presentation. I would like to ask regarding the GPS and the satellite. As we know that the Earth is constantly moving or rotating, so I would like to know that is the position shown from GPS data, is it relative position or exact position? Thank you.
Okay, it's a relative or exact position. Basically, what the information is distant. This transmit the information we have is the distance. So there are some algorithm that calculate the signal is the distance between the satellite and the point of the Earth. And once you get the position, it depends on how you're going to use the information. Yeah, and if you come back again to the previous question, yeah, how is posted to Pak Irwan, for example, how is you can, if I'm not mistaken, how you differentiate between the signal from volcano activity and then the signal from the tectonic activity. I think that kind of question posted to Pak Irwan a few minutes ago. And in that sense, as Pak Irwan mentioned, that the signal is we monitor a time series or a time series of a GPS, and then if you have a slight jump, as what happened when the inflation or deflation, then you think, or we think that that because of the some physical phenomena impacted to the station. But then what is the reference of that position? The reference is the previous time. So the early time, you use the time as a reference base, so it becomes relative, right? Because the fixed point is the time, the early time, and then you knew that the time, the displacement or the time series of the displacement is, let's say, 1 millimeter per month or per year, and then suddenly at certain time, at 1 month later, for example, it suddenly jumped. And the jump is related to the first epoch or the first data that you measure. So it's become a relative point. And that's being used in volcanic analysis, because as Pak Irwan showed in the slide, that you separate between time. So what is, for example, the first time is the first time period you only have, let's say 1 millimeter. The next period you have 5 millimeter, and then the next period you have minus 5 millimeter, and something like that. So that's refer to the first original time. But in the earlier processing, you will need to define the time. There are some model of the Earth, for example, called, the latest one is ITRF 2014, I'm not sure 2020 is right now published or not, but the latest available reference frame of the Earth, which can use, as you know, Earth is not really smooth shape. It has some how can I say, some irregularity in the surface, and then but to model, we need to there are some model to create a big picture of the Earth itself, or the Earth's size itself. It's called ITRF, International Terrestrial Reference Frame, and it's continually updating. And in our GPS processing, we're going to use that one because for example, the latest ITRF model is 2014, but the next, I believe, is 2020 or somewhere this year. And we use that model to get the position. And by having the location, as I mentioned previously, we use those position as either we're going to define our position in ITRF 2014, for example, or in the certain epoch for volcano. And if in the volcanic analysis, we use certain epoch as a reference. In different analysis, for example, earthquake deformation, sometimes you need a reference from ITRF 2014 because of different applications. So it depends on how you're going to analyze, how you're going to move forward with those data and what you're going to trying to solve.
Thank you, Pak Endra.
Yeah, you're welcome, Dian.
Thank you, Pak Endra. We have another question from Bu Lastari Harmita in the chat box. Perhaps Bu Lastari, do you want to ask yourself? You can also turn on your microphone. Otherwise, I can read it for you. So, Bu Lastari want to know how to estimate the volume of the material that released during the eruption using GPS monitoring. Perhaps you want to know the volume and correlation between the volcano deformation and the hypocenters.
Okay, Pak David. The correlation, how to estimate the volume. Example of the analysis have been shown by Pak Irwan apparently in the previous slide. He showed some volume using MOGI model, for example, and here I show some another example, for example, spherical. And in that equation, you will get the not just location but also the volume. So one model that presented by Pak Irwan was MOGI, and another model basically spherical. And which model, as I mentioned earlier, which model is we use our better fit to explain the data is depend on your data itself. So that's the modeling approach to estimate the volume and location. And second question, how the correlation volcano deformation and the position of hypocenter. As we know, it's volcano has a deformation character. Yes. Yeah, it's quite tricky because if you have earthquake, then if the earthquake is big enough, it could deform. It could create a displacement to your data. Let's say the 2004 earthquake, for example, the one that very big in 2004 Aceh, it creates a displacement up to 5 meter. So, but in volcano, you will not have those magnitude 9.4. But if you have, let's say, 3 or 2 magnitude earthquake, and it's just beneath or very close to the location, then it will create a displacement. But if you look at the if you look at the longer time period, for example, because the pressure is not just simultaneously, but as shown by Pak Irwan in the data, it has some period, for example, 3 weeks or 4 weeks, and then it's gradually different, have a different characteristic. So you have basically two different time period between earthquake that happen simultaneously and the one that have a longer time period for understanding the pressure source beneath the volcano itself. So you have to carefully look into the data. I think that's my answer. I hope it's answered the question, by the way.
Okay, we will move to the next question then.
Okay.
Okay, so we have question from Syed. How to apply the relativistic effect when synchronizing satellite clock with the stationary clock on the rotating Earth surface, so that it can forecasting when the volcanic occur.
Okay, so well, it's the technology part. If you have satellite above, as I mentioned, the signal deliver from the surface to our receiver, and it's just and to get the position, basically you need a minimum 4 satellite. Why? Because the 4 satellite is correspond to the time, and it's not just one satellite. Because if our previous slide in the GPS error, if you have only one satellite, then it cannot create it will not provide you an accurate position. So minimum 4 satellite, where the additional 4 will provide a time. So basically that's the number of satellite that you need to have in your receiver. So if you put a GPS receiver and you look at the satellites that probably only 3, then you will have a larger PDOP, or position dilution of position. And that is and if that's why right now, if I took an example in Indonesia, for example, the largest number is the Beidou satellite from Chinese government, and it has more than 16. And with having those many satellites, it will create a minimum error. Even so, if you combine, there are some studies by colleagues in geology department, colleagues of one group with Irwan Melano, that if you combine between the GPS and Beidou, so you will get a much more smaller error also. So having those combination, not just from GPS and also Beidou, and it can create a smaller misfit for your position and time. And I hope it answers. I would like to ask out. Okay, if I may to read the question, Pak David.
Yes, sir. Pak Endra, you can go to the next question.
Does the current GPS-based volcanic monitoring also utilize IoT concept? Yes, it's a very nice question, Rizka. So the idea of having those IoT, Internet of Things concept to the application such as volcanic monitoring is that we can have real data. And if you follow the last 2 days presentation by Pak Devi, they have already set up a system to deliver the seismic information lively, for example. And in Indonesia, the institution that maintain the GNSS data lively, transmit live to the processing unit in the office is Geospatial Information Agency. I'm not sure about the Geological Agency, but right now the GNSS station that maintained by Geospatial Information Agency, they can get real-time data. So having those real-time data, it just needs an add-on to understand any physical phenomenon. For example, if you have GPS data delivered to online, and then you just need an add-on of finding the source. And I believe the future presentation by one of our colleagues in France, Pak, I don't know how to spell, Pak Pucucul, how to spell that one in France.
Kerontang?
Yeah, okay, Pak Zul, you help me, thanks. I'm not sure how to spell that French name.
Francois, you mean?
Francois, yeah.
Francois.
Kerontang?
Bukan.
Francois, yeah.
Francois, okay.
Francois.
Oh, GDC, okay.
Francois has already set up a unit in collaboration with Geological Agency, but you will get a better view on the future presentation by Francois. But that is the idea of having a real time, because that real time information will be very useful for disaster mitigation purposes. That's the idea of having real time and understanding where is the source. As Pak Irwan mentioned in the example of one of the island in Japan, where he mentioned that evacuation take place at 7 a.m., the eruption at 9 a.m. So there is the idea, and if you can imagine if the evacuation even doesn't take place on 7 a.m., then there will be a lot of casualties. Thank you for the question, Rizka. And I will move forward to the next question. How is the deformation identified, whether by earthquake or by volcanic activity? I think I have answered this question. Question from Aldo, how deformation identified by earthquake. So you need to combine. We cannot just use one single information from GPS, for example, because the displacement of magnitude 2 or 3 is very small. You cannot see in significant. But the process of the physical process beneath the volcanic such as inflation, it will create a longer. It will happen at a longer time period, and you can see the trend. And having information from seismic, for example, as Pak Andri showed in a previous presentation, it will help you more with the analysis. Even so, if you have another data, so tomorrow Pak Asep will talk about GNSS, we talk about INSAR. The difficulties with GNSS observation is that you have to be in the field. You have to find a place where you can put a station, and then what happens if that location during eruption, the location was away by the magma or another effect after volcano, then that will happen. That sometimes happen in the station or GNSS station surrounding the volcano. So having additional data such as seismic and then INSAR, for example, it will help you understand the general view or the comprehensive view of the physical process that really happened. And tomorrow, Pak Asep will talk about INSAR. So let's wait and see how is the presentation and how is the explanation. Okay. Is it only, where are the where is there? Any question?
I think that was the last question in the chat box. So if anybody still has question from the audience, you can raise your hand, or you can also write your question in the chat box.
Okay, probably from myself, I want to add Pak David. Yeah. So if we have using, as I mentioned, and probably another Pak Irwan also mentioned, and another presenter also mentioned, so having a comprehensive or complete data set will help our analysis, because we have limitation with GNSS installation. As I think Pak Irwan also showed that they have 2 GNSS sites in Sinabung. If you have 2 GNSS sites, then it will be very difficult. So, but then if you have another data set, for example, INSAR, then that will be create additional data, because INSAR capable of capturing a widespread region without us able in the field. But the problem with INSAR is its line of sight displacement is not true displacement as GNSS output of GNSS. So, but if you have those 2 data, even though the GNSS very limited number, but with the additional INSAR, for example, and then supported by seismicity, then you get a better complete comprehensive view on the physical process itself. So I think that's the idea of bringing all this webinar. First of all, I think that's we hope that the participant will get a better view of not just from a single view from seismic or GPS or INSAR, but also from the whole perspective of understanding the volcanic deformation of volcanic physical process beneath the volcanic. And the purpose itself is if to bring those information for the mitigation purposes. And I believe the future next presenter also will talk about EOT thing that posted by Rizka, for example. So I think that's from myself, Pak David. Thank you.
Thank you, Pak Endra, for your very nice presentation, insightful about the satellite, the development technology in satellite, and how we use that in monitoring the volcano activity, and your insight on how to integrate not only one method, but several methods, geoscience method, in order to better monitoring the volcano activity, and also to we better mitigate the hazard that coming out from the volcano eruption. So I think on behalf of the committee, I would like to thank our 2 great lecturers today, Pak Irwan and also Pak Endra. And on behalf of the students, I would like to thank Pak Zul for organizing such an nice virtual classes which integrate so many experts in one course. So let's give a big applause for 2 our lecturers, Pak Irwan and Pak Endra Gunawan.
Thank you, Pak Endra. Thank you all.
Thank you, Pak Endra.
Thank you, Pak Andri.
Thank you,
Pak Zul, Pak Irwan, student.
So next, I will give it back the session to our boss, the one and only Pak Zulfa Kriza.
Thank you, Pak David. See you tomorrow. Tomorrow will be a bit earlier. We will start at 9 a.m. And tomorrow we have 4 lecturers that give us an insight about the remote sensing for volcano, and also a geophysical approach for volcano monitoring. Thank you, Pak David.
Ciao, Pak Zul. I will leave.
Okay.